Thank you very much. I think it's the best introduction that I have ever had. So I would like to thank also the conference in general and the committee that invited me here to be here today. Although I think to put a Greek as a first talker 9 a.m. in the morning, I think you don't know well Greeks. Anyways, I will give my best. So to try to entertain you for 1.5 hours. I have been working for 10 years almost now at IMEC. Yes, before I finished my PhD 20 years ago already. And I'm working all of this time on TFT and circuit design on different things. I started from pixel design and then later on I did other things, analog things, digital things. We will go through some of them today. So this talk is about, let's say, the future display as we envision it. As maybe you know, of course, in this field, that the TFT applications, TFT technology originates from displays. It started from there. Here you can see also two of the demos that we did in IMEC together with TNO and Call Center in the past years. But also imagers. There are X-ray imagers out there already for quite some years using TFT backplanes, mainly amorphous silicon TFTs. And lately, there are companies that have products on more complex, let's say, IC designs, which is mainly driven and targeting NFC, for example, NFC tags. We will talk about that also very briefly later. So what is the display of yesterday? I tried to make here a high-level block, let's say, diagram, how it looks like, the different, let's say, parts. You have a big substrate, glass or flexible TFT substrate where the display array is. And then most likely you have some integrated TFT gate driver, which drives the gates and the array of the display array. And then, of course, there are also silicon chips, either on the same glass or attached on PCBs that are connected with flex points to the display. What is the display of today? Very recently, actually, at SID 1 month ago, there are many different parties that presented displays with integrated fingerprints on all over the array, all over the display. We are able to read your fingerprint. You can put your fingerprint, also multi-fingerprint. You can put the whole hand and you can have the fingerprint readout. And of course, this puts some burdens on the peripherals. You see there are more silicon chips now that you need to have to read out this OPD array, an organic photodiode array that is also integrated there. One of the implementations, for example, has inside the pixel, beside the RGB, also an organic photodiode pattern there to make this happen. So in parallel, also, people are talking about putting extra sensors on the displays. Extra sensors that can be around the display, that can be inside the same pixel, on top of the RGB, or below or next to the RGB subpixels. And if you try driving all of this and reading out, you will multiply your rigid electronics around the display. And then you don't have any more a flexible display. You cannot dream anymore of a flexible display. So how do we see actually the future multimodal display? How should we see it and what should we target? We should target, besides having the integrated TFT driver, to have some kind of integrated readout of the sensors. We should target to have integrating control. We have digital logic there to control and to process, let's say, the data that you get. And maybe we should target also to have power converters on the display, where it's possible, of course. And I'm not saying that we will replace completely silicon. There will still be silicon there, but hopefully less. Of course, if you want to be a bit a dreamer, you will go one step further and you will have a future rollable display that can roll up on your pencil, on your pencil, let's say, size. And there you will again reduce further the silicon so that you end up having, let's say, the minimum size that allows this to happen. So what are the sensors that we are looking, and people have been looking around, and also in this conference we will later see many presentations about sensors. I mean, the first and most obvious is the temperature sensor, the pressure sensor, light emission or optical sensors that are already there actually, ultrasound haptic feedback, and maybe imaging, the touch fingerprint that is done with different ways, one of which is also the optical, and maybe the latest, which is more interesting, also the bio testing and the bio related, let's say, sensors. So what are the circuit blocks that we will talk about in the next sections that I have divided into 5 and are needed to make this happen? First, we'll talk about the sensor arrays and the pixels and how they are today and how people are improving the performance. The digital control and logic that we need to do some processing, to do some extra processing on the same substrate, on the TFT substrate, and what people have achieved and showed there that is possible. Then we will go more to the analog world. We will go to the analog interface, the parts, the blocks of circuit that are more in touch with the sensors, and do the readout. And then we will go also to analog digital conversion to bridge the gap between the analog world and the digital world. And at the last part, I hope we have time to also talk very briefly about some, let's say, latest applications where TFT have shown, and publications people have made publications presenting power DC-DC converters and neurons for HAI or ECG, etc. So how to implement? How do we implement this? How all of this come together? I already give a brief, let's say, intro on this, but let's make it more visual. So usually you have from the environment either light, temperature, or pressure, or something else that changes in time and also changes in amplitude. To interface that, you will need what we call an analog interface, which is also usually biasing, and using that block, you can get in the output some voltage or some current. Then you will need an analog to digital converter, which will convert this analog current or analog voltage to a digital form, a string of 1 and 0s, which represent a high or low, which later on will be used from the digital processing and control unit to do the tasks that you need to do more efficiently, faster, and also control back the blocks before that to do the right, let's say, the right tasks and the correct tasks, and many times also calibrate and improve the performance. To power all of this, of course, you need some power circuits, because all of these blocks might be that you have one power source and you need to operate them as efficient as possible. And they need different, let's say, power supplies. One block might need 3 volt, the next one might need 10 volt, and the third one might need 20 volts. So you will need to have let's say, power blocks, power management blocks to do all of this. And for TFT technology, an advantage that we always refer to is that we have area. We need large area to make a difference, to compare better to silicon typical technology, let's say. So we need, preferably we need to have a big sensor array. We need to have multiple sensors of the same modality or different modalities that are all over area, to have, let's say, an advantage against silicon technology that also can do all of this, and is doing right now all of this. So the metrics that we will talk about for all of this is the performance, of course, which can be either a speed or a gain, a conversion gain in some cases, the area that they occupy, and of course the power dissipation. Although some people might say that in large area electronics, the area is okay. And some other people also might say that the cost is very low for the area. So it's not really a concern. But still, you will see that in some cases, you really need to scale down to save in space and to meet the application's specs. So we will start first. The first section is about the array and the pixel and how we design an array of sensors and what has been made until now. The main application drivers here are two. Already one is for many years there, it's the X-ray sensors that people have been using and companies have been using amorphous silicon TFT, which is actually one of the oldest, let's say, out there. But also lately, as I said already, it's fingerprint. So fingerprint in mobile phones, for example, is, I think, the next driver for some years now. Both of them have specifications. Both of them have parameters that you need to take care of in order to make them work. But the main two, let's say, for these two applications are different. So for the X-ray, it's very, very important, the sensitivity, because you want to have as less exposure as possible to X-rays to take an X-ray, let's say, scan, to make a scan for your health. And for fingerprint is the high resolution, which you don't need, for example, for the X-ray. The pixels in X-ray are larger. For fingerprint, you need to have resolution. You need to go to the limits of the technology, actually, to push the technology to reach this FBI standard that you need to have a fingerprint, a certified fingerprint, let's say, imager and readout. And there have been demos, there have been products out there. From 2019, on the left, you see, for example, a demo of a fingerprint readout on the screen. 1 month ago, we had also several parties presenting multi-fingerprint readout under displays. At the same time, you see on the bottom left a display and a fingerprint all over the display. And lately, also, the last years, let's say, different parties are already advertising and have products of X-ray detectors with IXO technology. And we will talk about that also. So one step further also, we see that, for example, Samsung just 1 month ago in SID, they were talking, besides the fingerprint that they have already out there, they have a demo on the right, you see a multi-finger demo. They were talking about also next applications, integrated biosensor technology that can do electrocardiogram, they can do blood oxygen saturation measurements, they can do blood pressure measurements, and they can do glucose monitoring. So people are already talking about this from last year already, I think. This year also they repeated it. So it's coming, it's out there. But let's go a bit more technical now. We set the stage more or less. Let's go a bit more technical to see how this actually operates. You see here, I made a block diagram an array. Usually we have multiple lines, horizontal lines running through the array, metal lines that are, for example, the data lines, which is the lines that we will use to read out the sensors. And at the same time, we have vertical lines in this case, which are the select lines, which we use to select each pixel sequentially of each row, so that we will read it out and see what is the, let's say, the stored charge there. And on the left side, there is a zoom in, let's say, of one of the pixels. This is repeated all over the array, the same pixel all over the array. This is the most simple pixel that you can have. It's a passive pixel, as I call it, the passive pixel engine, which has only one transistor, one TFT, and photodiode. The capacitor there is actually the parasitic capacitance usually of the photodiode. Usually there is no extra capacitor needed inside the pixel. So the photodiode is let's say sensing the light and produces electrons that are stored at the capacitor, and then using the transistor and selecting each pixel, you read out each of the pixels one by one. And as I said already, we have externally on a PCB, on a rigid PCB right now, analog interface blocks that are reading each of these lines, and some multi-channel ADCs or multi-ADCs that read out and convert these analog values to digital. And at the same time, of course, you have some gate drivers, as we call them, that are driving the select lines and are selecting the select lines sequentially, row by row, to read out the charges. If we go again and focus even more, and we discuss, let's say, the specifications that we need to be aware of when designing a passive pixel, you see on the right, let's say, a very typical schematic of one row and one pixel, and the data line that is running through the array. Again, a passive pixel. People are talking and have need to make decisions on the front plane and back plane, for example. The front plane is the thin film photodiode. The back plane is the TFT technology that you need. That can be, let's say, from amorphous silicon to LTPS. And also from the front plane, it can be an organic, it can be a quantum dot photodiode, it can be an amorphous silicon photodiode. Then the next thing that you need to be aware of when designing is the sensor's performance. What is the EQE of the sensor? What is the dark current of the sensor? Numbers reported as 30% and higher are out there. And for the dark current, they talk about 10 nanoampere and lower. Then is the pixel pitch. We start from 150 micrometers for X-rays, and we go down at least at 50 micrometers, which is the FPI standard, or lower. Then very importantly is also the conversion gain, especially for the X-ray, as I already said. And then there are different, let's say, metrics, there are different units that are used depending on the scheme that is used, because as we will see next, besides the passive pixel, there are also other implementations that people use and propose. Then there is a noise level. The noise level of the whole system should be above a number of electrons there to be able to sense better. And of course, depending on the scheme that you're using, the readout scheme and the pixel engine, you have output that can be either in amperes, microamperes, or volts and millivolts. And of course, the speed, how fast you can read these pixels and this array. So now, how do we address this? How do we operate this? There are different phases. Phase one is to reset all the pixels of the array. Reset means that we have a known, let's say, VREF that you can see here, an ideal, let's say, optimized VREF that we reset all the internal nodes, all the capacitors inside the pixel are reset to this VREF. In the first phase. Then in the second phase, and also small detail here is, so not small, but something I didn't say is that we need to have all the select transistors open, so that they are addressed, and also this switch here needs to be also on, so that the voltage, the V reference goes into the pixel, under all the pixels. The second phase, we go the second phase, then let's say the switches now turn off. So all the pixels are now isolated from the external world. And immediately after that, the next phase is starting. Depending on the light that each pixel receives, it collects some charges here. And ideally, it doesn't leak out. So this transistor has to be has to have low leakage current when in off state, so that the leakage doesn't go out, preferably, because then you're losing information. And when the integration ends, we go to the next phase, where we actually again turn on the switches, this switch here now, the pixel switch sequentially, one by one, and we read out all the charges that are stored on all the pixels to the external, let's say, world. And this actually works. This very simple passive pixel works very well. And here is actually a publication 20 years ago, where you can see on the right a pixel taken using an imager of 127 micrometer pixel pitch. You can see also the top photo of the pixel. You can see the data lines and the bias line, the gate lines, the select lines driving through. This is one pixel. Here is the transistor, and on top is the photodiode. And also very recently, as I already maybe intro before, we have the previous one was using amorphous silicon. This one is now 2 years ago, I think, presented, but there is already out a product of an imager using IGZO technologies. And the company AUO is actually claiming that you can get 60% less noise. And they have this graph also here showing this, that with IGZO you can go lower in noise. So you will have better performance because you have better leakage current. And they're using these passive pixels there. So after so many years, they're using still one transistor and one photodiode on each pixel. Surprisingly also, besides presenting the advantages of using IGZO, they presented also at the same paper the disadvantages of using IGZO, although they solved it with a trick there. So the transistors, as you can see here, is a transfer curve of the IGZO transistor are shifting when they are exposed to radiations up to 6,000 or 600. And the VT is shifting. It goes, let's say, even 6 volts to negative. And they solved it actually very simple by just changing and reducing the select voltage when you turn it off from 0 to 6.5. So the VGS, let's say, will go to minus 6.5 here. So then the transistor will be turned off. And here you can see actually the readout from when it's in dark condition and when it's, let's say, in radiation condition. And you have a pretty good, let's say, dynamic range here, achieving this by biasing it with minus 6.5. But as I said before, they are besides the passive, they are also what we call active pixel engines, and they're coming mainly from CMOS imagers, where you can have some advantages. You can have also, you have more stringent and more strict conditions for the TFT, because now you need to use it as an analog, also as an amplifier. As you can see, there is an amplifier here. This is implemented in different ways, as we will see just in the next slide. But you have advantages as increasing the conversion gain. In the passive pixel, the conversion gain is very small. You get best case for one transistor in, for one electron in, one electron out. Oops. You want to increase that. You want to have better conversion gain. You want to have more electrons for one electron in to have better resolution. And you want also the noise to go lower. And in some cases, we have also simpler readout ICs. So the readout gets simpler and cheaper. There are two main, let's say, pixel engines that you can do for active. Is what we call voltage mode and what we call current mode. The most obvious advantage of the current mode And the difference between the two is actually the speed. In current mode, you are much faster, which is very important, for example, for X-ray, where you want to decrease the exposure time. But there are other differences also, which I have listed here very briefly. Besides the speed, let's say, the other difference between the two is that in current mode you can have higher charge gain than in the voltage mode. And in some cases you can have lower noise, for example, for the voltage mode. And how do we actually implement this? How is the pixel engine? The main difference between the two, you can see here, is the select transistor. So you have now at least a 3 transistor pixel in both cases. You have the amplifier, which is connected the gate on the storage node. You have a reset transistor, which you use to reset at the beginning, as if you remember. And then you have the select transistor, which is connected to the amplifier, either from the source side of the transistor or from the drain side in the common mode pixel. So in the common mode pixel, we actually have a common source amplifier, which means that we don't degenerate the amplifier as we do for the traditional, let's say, voltage mode pixel, which means that we don't decrease the gain. So the gain by definition is larger at the current mode pixels than the voltage mode pixels, and also the speed is usually much better because we have a constant current. And people have been publishing on this. People have already for almost 20 years talking about improving the passive pixel. The team in Canada, Professor Karim, for example, even went a step further and replaced one of the transistors, the select transistor, with a capacitor. And what they did, actually, they even fabricated and tested this. What they did is to use a pulse on the read line here, which runs through the whole array, to pulse the capacitor and read out the charges that you have on each pixel. In this case, again, the gain of the pixel is equal to the gain of the amplifier of T1 here in this case, or T amp, where in the 3T transistor voltage mode, as we already said, you generate the gain of the pixel by let's say the resistance that is caused and seen from the select transistor that is in the pathway to the output. In this case, you don't have that. So you have a faster pixel. So that was the intention of this layout, to have a faster readout. But still, as you can see from the measurements that they did, you still need 12 seconds readout to get some kind of the dynamic range between the dark response and the response under light. Second is the current mode, and here you can see actually implementation that we did in IMEC in a consortium some years ago. We actually implemented the current mode TIA to have a fast readout. You can see let's say the schematic, the basic schematic here. Besides the current mode pixel, we had also transimpedance amplifier. We used different way to read out the charges, and this is because of the capacitances. When you go larger on pixels, you can simplify the readout. As I said before, you can simplify the readout and make a cheaper readout using just the TIA and the resistor. And on the top, you see photos of this and a photo taken by this imager. And the performance is outlined on this table. We have a 100 micrometer pixel. We used amorphous silicon as a backplane technology. We have a organic photodiode on top, and also we improved the noise. Actually, there was also at the same run a passive reference imager which had 4K noise. We achieved almost 25% lower noise there, which means better pixels. And now we have actually a gain on the pixel compared to the passive pixels from the incoming, let's say, say charges, we get a current out of it. If we go to the fingerprint now, as we said before, we need to scale down. We need to have 50 micrometer pixels, and to do that, again, we had to tweak the technology. We had to create a dual gate technology to go from 3 transistor active pixels. You see the layout down here, to have a 50% reduction in order to get a 50 micron pixel with only 2 transistors. But now having also a backgate on the transistors, and especially this backgate here of the amplifier is used actually to turn off this transistor and isolate the pixel from the data lines. Because when you bias this, let's say when you bias this backgate with the voltage, you are shifting the VT of the transistor, so you're turning it off or turning it on when you want. Of course, you have a penalty. You have again a degenerated source amplifier. The gain is lower than in the current mode, for example. But you have a price to pay to reach this 50 micron pixel. And we actually fabricated this and measure it. You get below 10. We got a 10 below 10% nonlinear error for a range of, as you can see here, of 1 volt more or less, output range, I mean. And you see also that the speed is relatively in good shape, below 40 microseconds. Even that it is a voltage mode, let's say pixel, the design allowed to get this response. Yes. So very recently also we saw a publication at SID where they want another step further, and they use the 4th transistor in the pixel. It's this transistor here, is the transfer transistor as we call it, where you isolate actually the photodiode from the rest of the pixel. And this has many advantages. This is let's say the basic pixel, the common pixel that is used now on CMOS imagers. You can increase and improve many different parameters of the pixel and have better, let's say, performance. Although it's not clear from their presentation and the paper, if indeed this is a PPD pixel, as we call them, still you see amazing results, even though the OPD that they are using is very small. It's only 1.5% of the total area of the pixel. Their pixel is 50 microns, so they have a 6.1 micrometer pitch pixel. And I think this architecture actually made it possible to have multi-fingerprint readout and also have this very good display at the same time. Nevertheless, summing up all of this, I have put here a table where you can see the progress through time of the size. You can see the sensor that is used, the different architectures that have been proposed, and what is the application. And also I have included, let's say, a reference list here for all of this for your convenience. And with this, we will go to the second part, which is the digital design, which is actually the last part of our, let's say, of our flow. We started from the beginning, from the image array, from the sensor array, and now we go to the last part. And here, actually, the main drivers of this from the industry side was the NFC tags. So they are now, since some couple of years ago, they have actually products out there, both programmatic and also AUO. They have NFC tags out there, which they are promoting for customers that are working and are ready to be used. So what is actually digital design? What is digital logic, Boolean logic, as we call it? Here you can see a schematic of the basic gate, an inverter gate, and on the bottom you see a truth table of this. What is the input and what is the output on the corresponding input? So we can have 2 inputs. We can have a high, let's say, low, 0 as we call it, or 0 volts in reality, or we can have a VDD, so high voltage, which is 1 in the logic. And then what this gate is doing is also inverting whatever is at the input. So if you have a 0, you get a 1 at the output and the opposite. How is this implemented with transistors in complementary technologies like CMOS, for example, silicon? You must have both P-type and N-type to do this, and you connect the P-type to the VDD to the highest voltage, and the N-type to the ground, to the lowest voltage. And on the bottom, you see actually a graph showing the correspondent output to inputs that you get from 0 to VDD to the highest voltage. You see that initially the output is high, as we said, and then gradually it goes to 0 when VDD is low. And what are the important parameters? How we quantify the performance of this block is to the two first, the noise margin, what we call noise margin and gain. And what is noise margin is actually what is the amount, let's say, of voltage where the gate is stable at the output when it's high or when it's low. So as higher this is, as more stable the inverter is. And the second one is the gain. So the gain is actually the slope of the transition here from high to low. And as sharp this is, as better, because then you have better noise margin. And the third one, which is very important also, is the propagation delay, which is the delay, the time that is needed for the gate to respond to an input. And this is very important for bigger designs where you want to have fast processing. So as fast it is, as better. So there are other gates also, many other gates actually. Here I also have listed, let's say, 2 that are very, very common, and also the truth tables and the symbols that are used for your reference. But let's go to TFT now. So as I said, in CMOS or in LTPS technology or organic TFTs in some cases, you have both P-type and N-type, but this is not the norm of TFT. Usually you have either N-type or P-type, so you need to find a way somehow to replace this P-type in case you have N-type or the opposite. So people have, let's say, designed and proposed different solutions. I have 3 here. The first one and most, let's say, cheapest one is the direct load, as we call it, because you have you use two N-type transistors, and the second one, the one that's connected to VDD, is now diode connected. So the gate and the drain are connected together, which we call diode connection. This works. So you see the transfer at low you get high, and at low input at high input you get low. So you're inverting the signal, but the performance seems very poor. The noise margin is too small, which means the reliability of this will not be good enough, which means when you try to make a microprocessor, it will not work, or the yield will be very low. So a second thing that people have proposed is to have a dual gate technology, and you use the back gates of the transistors to actually shift the transfer curve and put it to the ideal place, for example, which is the middle one here. And then you have a better noise margin, and you reduce the power, for example, in some cases. And the third one is to have a resistor. Both this solution require another device in your technology, which adds some cost, but you get what you want, or close to what you want. Another solution, very popular solution, which you don't need extra devices, but you increase the size of the logic gate. You have now 4 transistors, and you have 2 voltage rails, 3 actually with the ground. You have 1 extra voltage rail, and you have 2 extra transistors. But then you get a very good output transfer curve. You have very good noise margins. You reduce the power in some cases. when the V bias, for example, is 25. Like I'm doing. But as I said, you increase the size of this. And in IMEC, actually, we have used this in two very good demos. Besides other things, we presented some years ago the first NFC tag that is, let's say, communicating with a commercial phone. And also we presented the first, let's say, tag, thin film tag that is powered from a PV, from the display itself. So no other power sources were used to make this happen, and transmits to the touchscreen some data, a digital code, in which we can see here by this line moving, which indicates that some data is sent to the touchscreen itself. And this was actually on the cover of the Nature paper, of the Nature journal years ago. But of course, there are other logic also, more niche logic, let's say, people have suggested throughout the time. And here you can see one of them. And this is what happens when you give an analog designer to design a digital block. He puts a capacitor here, he puts a feedback loop, he improves the performance, but this is way too big to use in a digital logic. But I learned that when I went to IMEC, and I wanted to make larger designs. There are other also, what we call crossover logic. Again, very low power. We improve the power, we improve the response. You can see the transfer curve, very sharp transfer curves. And my colleague also made actually a 4-bit adder demo, which was working using this logic. But you need a negative ion technology to do that. Otherwise, the performance goes down. There is also what we call dual input logic. This was let's say a logic that we wanted to reduce the number of transistors when you use the pseudo-CMOS technology. And in this case, we use again the backgate to have the inputs instead of transistors. So we reduce the size of each logic. And here is a list of different cells. And the area that we were occupying in the, let's say, standard pseudo-CMOS and the dual gate pseudo-CMOS, we noticed a 20% array reduction. And my colleague also demonstrated a 30-bit code generator of this working with even 1 volts. And last but not least, there is also as I said before, the resistor logic. There is also a 2-stage resistor logic on the same, let's say, pseudo-CMOS logic where you use a resistor. You have improvements in the noise margin compared to the 1-stage, but you pay some penalty, especially for low voltage, for the delay, it's a propagation delay and the power. Again, there was a demo with a large circuit, a 4-bit adder working up to 1 megahertz with this logic. But then LTPS comes. LTPS comes and makes things easier. You see here comparing actually the state-of-the-art pseudo-CMOS logic we have used in so many demos to a, let's say, LTPS 3-volt operation. And you compare the two, and you have better noise margin, you have less power. If you measure the current, you will see that the power goes down almost 2 orders of magnitude. And on top of that, you don't pay, let's say, in power. So if you make a ring oscillator, sorry, in speed, if you make a ring oscillator, even though the power is lower, you see that you get, let's say, 15 times faster gates, which means 50 times faster logic or processing, at least, even though that we're comparing here 2 different nodes, a 1.5 node to a 2.3 micrometer node. You get sub-nanosecond gate delays. And here's a table, let's say, more fair comparison, because all the rest were different technologies, different logics, comparing the two main, let's say, technologies right now, the LTPS and the IGZO. You see, even when you make on LTPS, when you make the pseudo-CMOS, let's say, state-of-the-art logic, the dual gate diode load, and the CMOS, let's say, logic, you still see that the CMOS is beating. The noise margin has a very good stage delay, has very, very low power, maybe a bit more area, but this depends also on the node that you are. If you compare, for example, to the IGZO, where the node is lower, it's 2 microns, you have less area. Even though you have a resistor, you still have very good noise margin, though. So I tried a bit to make the comparison here, more fair comparison from data that our PhD student actually is putting his PhD thesis that will be out there this year. And of course, this is not enough. You want to go more complicated. You want to build big processing units. You want to have microprocessors. So you need what we call a physical implementation for flow. And this is it's an example for LTPS. You start from a CMOS library. You use a tool, which we call synthesis tool. You reduce the cells. You again remove some complex cells that you don't need. You do a schematic and you characterize each of them, and then you end up with an LTPS loop. And then again, you use a tool that is called synthesis tool, and you go to a gate level schematic, and you use a place and route tool, and you make the layout of, for example, a 6502 microprocessor. Here is the list that we use, for example, for the LTPS microprocessor. 6502 is a microprocessor that was used in the past in many different products that we know. We had 2 implementations, one with LTPS and one with IGZO. And you see the comparison here of the power to the speed. You get, let's say, 10 times and even more. 10 times and even more, let's say, speed, and 200 times lower power from using LTPS technology. You see also some pictures of the chips here. The LTPS actually are 2 processors here. You can see them here. Still, the size is a bit bigger because the node of the IGZO is lower. But the price that you pay is much larger in power and speed. And actually, we made also a demo with this. We played the game, the snake game from the 80s. You can see it here, going around. The snake is going around. It's the 1111, and the apple is the EE. We had also a demo at SIT. There is a video on YouTube you can watch. And here is actually again a table of the 3 latest microprocessors, also from ARM. They had presented a 32-bit ARM processor using an IGZO node, a pragmatic IGZO node. And also on the left side, you see actually the first one that was presented in 2014 using IGZO and organic to have a complementary technology. And with this, I will go to the analog interfaces. There are 2 parts here. First is the, let's say, the sensory dot, and then is the analog to digital conversion. And the basic block that you need to make an analog interface is what we call an amplifier, preferably a differential amplifier to reduce noise. I have here a schematic of the very basic, let's say, amplifier that is used in CMOS technology. Again, you have the same problem here as before. You need both P-type and N-type, which are not available usually not available in the TFT technology using IGZO, for example, or amorphous silicon. So either you use a resistor again. Another option is to have a resistor, but this also requires to have another device there, or you again do a diode load differential amplifier with all N-type transistors, for example, or all P-type transistors. But you will have to be careful for each of them to design properly and improve their performance so that you get actually amplifying stage. So, for example, what we call low transistors are T3 and T4. What we call the input transistors, T1 and T2. We apply the inputs here, usually an input and a reference. And then we have the current source, which is T0, where you use this to bias the whole amplifier, to have a constant current and to bias the whole amplifier. So you need to be careful for the output resistance, as we call it, and the GM, also for the input transistor, but also for the load transistors, which is the transconductance of the transistors. And I have put here for reference what is GM and what is output. Is a change from IDS for changing VDS, the R output, especially for its saturation. And the GM is the change of the IDS, the slope, in other words, on a change in VGS. Yes, so if you go now and design this unipolar differential amplifier where you have only N-type transistors, you will see that your gain is given from this equation, which is the two GMs actually, the GM of the input transistors to the GM of the output of the load transistors, plus the output resistors here. If you try to minimize this as much as possible, the two output resistances, for example, then you will have, let's say, the GM over G4 will define your gain. So you want the GM2 actually to be much larger than the GM4. This is practically done by having much larger transistors, T1 and T2, over T3 and T4. But of course, there is some limit because these are not actually zero. And to do that, for example, you can have a backgate. Again, a backgate, you have a dual gate transistor, and you bias this backgate properly, for example, in this case with 0, and you decrease the output resistance, you decrease the slope. And you have better, let's say, R output for your transistors. Then if you bias the transistor again with positive or negative, you will see here we have now the plot of the IGS over VGS. So we have an indication of the GM, how the GM is changing. You will see that biasing the backgate with positive, you shift the VT to the left. Biasing to the negative, you shift to the right. And also you change the ions. The ions are changing compared to the middle one, let's say, which is VG0. And if you go also a step further and you sort backgate and front gate, you will see that you get even better performance. You will get better sub-threshold slope and also much better, almost an order of magnitude better than in other cases, ion current. And if you actually make the calculation of the GM, you will see what is a bit obvious here, but you will see actually with numbers that you can go up to 10 times larger GM, which will improve your gain of your amplifier. The minimum can be somewhere around 2 times. It depends on the current that you bias. For the same current, you see here is the normalized actually GM over the current. For the same current, you see with the red, which is the dual gate, sorted dual gate, backgate and dual backgate and front gate sorted case, at least 2 times larger GM, which means at least 2 times larger gain from your differential amplifier of the same size. And last but not least, another maybe problem that you want to tackle is the VDS drop over your current source. And we have improved that in the past by using, again, the backgate, by changing the size of the backgate. You can see here the plots of the normalized current to the VDS of the transistor. And you see when you increase the backgate width, you drop the VDS. So you need less VDS. In this case, for example, the green curves need 2 volts only for this current source to work compared to the 7 volts that you need in the blue case, for example, because there is where the current is stable. In the other, if you go lower, you will see that the current will fluctuate, which you don't want from the current source. You want the current source to have a stable current. So if you put all of this in a design and you compare it to the single gate case, I have highlighted here with red, I'd say the changes that you will do for the dual gate, how you will connect your back gate for the different transistors. If we start from the top, you will see that for the low transistor, for example, you short your backgate to the source to improve the R output, in other words, to have a VGS of 0, as we showed before. For the input transistors, you will need to tie them to the input, to the front gate, the backgate to the front gate, because as we show in this way, we improve at least 2 times the GM, so the GM is improved. And for the current source, again, you need to have a large, actually, backgate, as large as possible, and also to connect it to the ground, to the source of the transistors. So you make these improvements. You also calculate, again, the gain of the for the 2 stages, and you see also numerically, but also let's say equation-wise, you see that you have an extra, a very extra GM here that comes from the backgate of transistor 2. The other terms are all the same, which means from definition, the dual gate, let's say, gain would be larger if all the rest are the same, all the sizes and everything is the same in the transistors. But if you put on this also some designs, let's say optimizations that you do, you will go higher. So these are actual measurements from samples, and you see from the dual gate you go 2 times and more in some cases of gain. But is this enough? Is 3 volts over volt enough? Is 10 dB enough to have an amplifier stage that is useful? The question in some cases is no. So you go and you propose new things. People are proposing new designs, one of which is also this cross couple. So you use the backgates to cross couple to the outputs. And this applies a positive feedback on the transistors, on the input transistors, which if you calculate here, let's say the small signal gain, DC gain, you will see that you actually now subtract the GM of the 2 transistors from the denominator of the GM4 of the low transistors. And we have to be careful, of course, here that this doesn't become too negative, because otherwise you will have a negative effect on the gain. But it has to be close enough to the GM4. So if you design carefully, you will increase your gain tremendously. You will go to 55 dB. But the problem here is exactly because you're designing too carefully, you have a very limited input range of only 5.5 volts. So you can use this amplifier only on a very limited input, let's say, range. Another proposed, let's say, technique, which actually happened many years ago in the 80s, first time, and then came also to TFT from various different groups, many different implementations out there. I will show a couple of them here today. You apply a positive feedback again from the outputs to the load transistor. And in this case, you get a gain which is represented here in this equation. And here again, you have to be careful that this term, it doesn't become larger than 1, because then you, or 1, because then you will have an unstable system. At the same time, you improve, of course, also the output resistance, which is now actually the parallel of the 2 output resistance of the input and the load transistors with this design. So we implemented the IMEC. We proposed one, let's say, feedback block. So this is, let's say, a circuit that we proposed to make the feedback. We also proposed to actually couple now the front gate and the back gate. So we use the GM of the back gate also of these 2 transistors to improve the gain. You can see the layout here of the different parts of the circuit. And we measured this actually, and we measured also the frequency response of this, and we designed carefully, and we saw that especially for the L5 version, the gain goes up to 42 dB, and also it's stable, so it has a phase margin of 52, which means that the circuit will not start oscillating when you use it at the output. There are other also proposals. Very recently, there was a very good paper out there analyzing this in every detail that it can be. I try to summarize a bit here what was done. You can find the paper if you're more interested to learn more about this. As I said before, it's very important to have a stable amplifier, a stable operational amplifier. And in the positive feedback case, you have to take care so that the gain doesn't become one of the feedback loop, because otherwise the total gain of the structure goes to zero. So you can see here the low transistor. So this is the low transistor that we are talking about for so long now. And the rest of the circuit is now just implemented here and depicted with one current source. So what did this group propose from KU Leuven was to use actually another 4 transistors here as a feedback loop. We have actually 2 feedback loops. One goes from the TF3 transistor, and the other one goes from TF4, TF2, and back to the gate of this T1. And this way you create, let's say, a feedback loop. You have a common drain transistor here. You get the output. This is the output node of the differential amplifier. You feed through to the input of the low transistor. You have to design so that from the analysis that has been done in the paper, you can read it. You have to design so that the transistor 3 and 2, so these 2 transistors here, a GM that is smaller of 2 times the transistor the GM4, so that the gain of the feedback loop is smaller than 1. And this way, the gain will be guaranteed smaller than 1, and the circuit will be stable. So they did that. You can see a photograph of this differential amplifier. And again, they reported and measured this, and they're reporting a bit more than 40 dB gain, but at the same time, a very good phase margin of almost 100 degrees, which is actually the best out there. And that is because they really analyzed the circuit, all the poles of the circuit and the zeros, and they put them and designed them the correct way to make it happen. There are other loads out there, of course. Unfortunately, there's no time, let's say, to go more into. We talked, let's say, about these first 2, the normal diode load and the feedback. But there is also, more than 10 years ago, the PhD student and IMEC actually proposed this bootstrap load, where you use a capacitor to have a feedback from the source of the transistor to the gate. Again, you need to design here so that this capacitor CB is large. So at high frequencies, you can have a very large, and you can boost your gain a lot by using, because you are shorting actually, and you are essentially creating a 0 VGS load here. And you have a large gain. You can get large gains in this way. But you need, as I said, a large capacitor, a really large capacitor to do this, so that you can push as much as possible closer to DC at this point. Because at the same time, again, there is a technology with lower mobility, so you need to take care of the frequency, be low enough so that it can operate. Otherwise, in lower frequency, it's just a diode load connected here, diode load, let's say, amplifier. So the problem with this actually is the large capacitor. It can work, but you have to have large capacitors. There's also a 4th one that we briefly can touch upon, is 3 transistors in series. You need double gate technology to do this, and you get the benefit that you get out is a very high output impedance. To go one step further, until now, all the, let's say, the publications out there, people are reporting usually only the best, let's say, measurements that they are getting. We went last year, let's say, a bit further than this and step ahead. And we actually measured several samples of the same design over several wafers, but not only measured, but reported them at IDW. This is actually using a fab technology, pragmatic IC technology, which is available for universities also. We only use 17 transistors. Is a positive feedback again design, which is very robust in general. If you know to design for it, you can get good results, and we got good results. We got 42 dB, which is the range that you should expect using positive feedback with only one stage of differential amplifier. And we reported also that the spread is almost 3 dB here for the gain and the median offset, and what is the spread of the median offset, again, below 70 millivolts. And we got very good performance also, around 52 phase margin, and a very good also gain bandwidth, as you can see on the plot here. And here is actually a summary of all of this, of the state of the art of IGZO op-amps, especially, and how they progressed. And again, if you go now to put also LTPS in the mix, and you compare the gain that you get, and also the input offset that you get using LTPS or IGZO. So we have one IGZO here, say operation amplifier, the one that I just showed before, and 3 designs using LTPS, and you get larger gains, even with an op-amp that has less transistors. Only 7 transistors compared to 14, you get almost 55 dB. And in some cases, better also, say, spread of this gain. This actually is larger than the IGZO, but this is for, let's say, for a very large operation amplifier with very small voltage. Shown here, and also for the input offset, there is no discussion. It's always lower than the one that you use at IGZO. And here are all the references. Of course, we don't just stay designing some blocks. We try to do useful things with this. There is a PhD working at IMEC. He has used PVs, monitored PVs, the temperature over PVs. He has built the system. You can see the system here, using a max, a buffer, and SPI module, a complex system. Here is the whole design, a picture, and he actually measured it in a real environment for 5 days. And he compared it actually to silicon only readout, and his TFT, let's say max plus buffer. You see the curves overlapping pretty much up to 20 degrees. Here we see some deviation, which we need to take care in future, let's say, designs. And with that, I will go to the last part, which is the analog to digital conversion, a bit faster. We have different architectures, basic architectures. I will focus mainly on the SAR topology and the sigma delta topology, because with SAR we get low power, and with sigma delta we get very good, the best resolution we can get, which were important for some projects we were working on. So that's why we targeted these two. And actually, a turning point for me, especially, was this publication that was almost 10 years, 14 years ago, where the group in Stuttgart used actually a 3-volt TFT technology, organic technology, to present SAR ADC, a 6-bit SAR ADC, using the C2C topology, giving very good responses below 1 LSB. Here you can see actually the result they give. Using an inverter-based comparator, coupled capacitively, and also a calibration. A very, very good work using organic DFTs. They very good paper, actually. They're outlining all the problems that they had and how they dealt with all of them to make it work. Impressive work. So we had a similar project a bit later. We again used the SAR, let's say, topology because of the low power. It goes for an RFID chip, and there the power matters a lot. In this case, we use the differential, let's say, input now comparator with differential C2C networks. We had a version with on-chip digital control and a version with off-chip. And the one that I will show you just now, the one with off-chip had also the references on chip. So everything and the input bias was on chip. Everything was on TFT. How does it work? How does the SAR, let's say, operate? What is the principle? For example, for a 4-bit, you will have 4 main phases. You can see the reference, the input reference here, and the time on the x-axis. For example, if you have an input that lies here, you start from the reference. You have a reference. You start from the middle of the reference. You compare this to the VO1 using a comparator. And if you see that it's above, you put a 0. And then the next thing that you do is that you pull down 1/4 of the VREF, your reference. And then you compare again. And since you are below, you get a 1. And then what you do, since you get a 1, you go higher. You go higher, but 1/8 of the reference now. So you binary reduce, let's say, the reference voltage. You start from the half, you go to the 1/4, and then you go to the 8th, and then you go to the 16, and you compare again step by step, and you get the output. How do you implement this? How did we implement this? So you reset your DAC, you sample your input, then you set the high for bit n, then you compare, as we said, and depending on the output, you go high or you go low. You change the bit or you retain the bit. Here is a time diagram of all the control signals that you need and the output of the comparator. You sample first, you reset and you sample. Then you start from the bit 5, the largest bit. You pull it up, you compare, you see that it's 0, you retain it. So since it's 0, you retain the bit. And then you go to the next bit. You go to bit 4, you again pull it up, you compare, you see if it's higher or lower. Since now, this time it's high, you toggle the bit, you pull it down. And you go to the next ones until you reach the last bit, and that's how you get your output code. And you reach, gradually, you successfully approximate your input in this way. We made this, here are the results. We also, as I said, made the full system. We integrate the digital control, we integrate the references. You only need a power source and a clock, and then the input. We actually connected it to a sensor, a printed sensor, temperature sensor, and put it on a hot plate. We measured it, we put up the temperature, we measured it, we got this output. 1400 TFTs, 40 capacitors for this design. If you upgrade your semiconductor, we use better mobility, you can go faster, you can retain your performance with good design. Yeah. And if you want to go even faster, you will have to change, for example, topology. We did a design with pragmatic technology. You can see here, say, 6-bit response. We implemented and we measured the comparator of this technology. We reached 100 kilohertz operation. And again, we reported and measured many different comparators for the first time, having a median input offset of only 20 millivolts. Another group actually had the same idea, the same topology almost. They implemented this before us and they published it last year already. They showed good results. And last but not least, when you want to go to larger, let's say, resolution, more resolution, you will have to again change and use another topology. And if you use also LTPS, you can go faster. Here's a very typical first order sigma delta ADC that we made with a sample and hold circuit as an input and last output that is needed. Sample and hold, the charge integrator and the last output. And if you want to see a bit how this operates, you have a node B here that is pulling up to the reference. And whenever it reaches the reference, there is a comparator that triggers. The closer to the reference, the more the outputs that are triggering here, the output. And that's how you use this code that you're getting at the output. You decimate this code and you get your digital code out. You actually fabricated this, designed and fabricated. Here again, we are reporting 8 samples measured. The DNL and the NL is plotted. DNL looks okay for 7 of them. Only 1 was not okay. The INL, we noticed some problems, some non-linearities due to the input, let's say, summon of hold circuit. We think that is the problem. Nevertheless, we are able to actually detect 1 millivolt using 7 out of 8 of the samples at this speed and with a 2 millivolt of power at 10 volts. And with this, I will, let's say, conclude the ADC part. Also, here's a graph, very complex graph. I don't have, unfortunately, time to go through it. I try to put all the TFTs that are out there, comparing the signal and the resolution. And with that, it's section 5. As I said, DC-DC conversion also possible. Neurons with TFTs, yes, and also ECOGs. So all of them publications out there showing the road to something new. And some last words to summarize all of this. We worked on something that we call Sense and Actuate platform using TFT backplanes. In IMEC, we not only, let's say, work to improve the sensor and actuator, we also work to improve the circuits, to increase the performance and simplify the CMOS ICs that are needed. The holy grail, of course, is to combine the two and co-design the two so that we have the best performance out of it. And that's what we try to do. We have been using until now lab technology. We are moving to fab technology. The reasons are a bit obvious. And with this lab technology, especially the LTPS, you can get maturity technology, you can get developed PDK that we have inside IMEC throughout many runs now, higher mobility and CMOS. You can make many different, let's say, demos that are not only, but can you have large area ultrasound for medical systems. We had some talks last year about this, medical imaging. You can have large area optical imagers. You can have electroweighting with TFT matrix below. Here's a summary of all the different applications and say the vision. And this is the team, many of which I showed you is let's say, a collaboration or a work of all of these people here. We are open to collaborations in general. And I'm looking forward for any questions you have. Thank you very much.